Let's get back to talking about the properties of elements and how electron configurations have an effect on the properties of elements. We've already discussed, at least briefly, the reason why the periodic table is arranged the way it is. So it's arranged based on the electron configuration. We have the S block, the P block, and so on. The elements are arranged according to that configuration. Now we're going to talk a little bit more about the properties that we can predict using the way that the periodic table is set up, using the fact that all of the elements in this row, this would be the alkaline earth metals, all the elements in this row, or column, have similar configurations, and so therefore they have similar chemistries. They'll have similar chemical and physical properties. So we're going to look at, I believe, 4 different properties for 4 different things that will change from one side of the periodic table to the other and up and down the table as we look at excuse me, as we look at how the excuse me, something stuck in my throat tonight. So we're going to look at ionization energy, electron affinity, metallic character, atomic radius, and then electronegativity as well. So I guess 5 different things that are going to vary across the periodic table. Before we do that, though, I do want to introduce us to the idea of effective nuclear charges. And the reason for this is that effective nuclear charge can be used to help predict what will happen with most, if not all, of these properties that we're going to be looking at. Some it's a little bit more difficult to use than others, but especially the first few that we're going to look at, the first 2 properties, it's actually fairly easy to see how we can predict how those properties change across the table if we understand how the effective nuclear charge changes across the table. So what the effective nuclear charge is to put it in as simple terms as possible, it's how strongly the outermost electrons can see or feel the nucleus. So electrons have a negative charge, protons in the nucleus have a positive charge, there's an attraction there between the two, and the effective nuclear charge just saying essentially how strong is that pull? How strong is the pull of the nucleus on those outermost electrons? This will vary across the table because those outermost electrons have their view of the nucleus blocked by the core electrons. So the electrons that are between the nucleus and the outermost electrons, the valence electrons, those core electrons block the view of the nucleus, making the effective nuclear charge smaller. And that blocking of the view, that shielding as we're going to call it, of the nucleus, is going to change from one part of the table to the other. So this is the equation we're going to use to describe the effective nuclear charge. And I think, yes, we have a more detailed description here. So we have Z star, which is the effective nuclear charge, is equal to Z, which is the atomic number, which is just the number of protons that an element has, minus the screening constant, which is essentially how much of the nucleus is being shielded. Now there are a whole bunch of ways to calculate this screening constant. If you want to get super complicated, you can get pretty much as complicated as you want. And I'm talking like needing a supercomputer to do your calculations type of complicated. We are not going to do that. We are going to be as simple as possible. We are going to use the number of core electrons as our screening constant. And so it's not actually going to be constant across the table. It will be different for different elements. But if you are looking at sulfur, for example, it's only going to have one value, and so that's why we call it a constant. You're not going to have one sulfur where it's one thing another sulfur that's something else. Not without dramatic changes to that atom. So anyway, so the effective nuclear charge is just the number of protons minus the number of core electrons. So for aluminum, as an example here, aluminum has 13 protons. That is the atomic number of aluminum. And if you work out the electron configuration for aluminum, you will figure out that it has 10 core electrons. And again, the easier way to do that, other than writing out the whole electron configuration, is if we go, well, it's kind of hard to see it there. If we go back to a periodic table here, everything in this column has 1 valence electron, everything in this column has 2. All of the transition metals, we're just going to say those have 2 as well. It is actually a little bit different from one to another. There are exceptions, if you remember, and actually you can see the exceptions here, but we're just going to go ahead and say they all have 2, and then 3, 4, 5, 6, 7, and 8 valence electrons. And so it's actually easier just to figure out how many valence electrons it has and then just subtract that out. So in the case of aluminum, it has 13 electrons, 3 of them are valence, and so you have 10 core electrons. If we look at a few other ones here, so silicon, if we do silicon, silicon is number 14, am I remembering that right? Yes, 14. So it has 14 protons. It's going to have 4 valence electrons. So its effective nuclear charge is going to be 14 minus 10, which is 4. So it has a slightly higher effective nuclear charge than aluminum. What that means is the outermost electrons feel, so to speak, the nucleus a little bit more strongly in silicon than they do in aluminum. If we move on to iron, iron is 26, if I remember correctly. There it is, 26. And it is going to have 2 valence electrons, which means that it has 24 core electrons. So 26 minus 24 gives us 2. So it has less, a smaller effective nuclear charge than either aluminum or silicon. So its outermost electrons feel the nucleus less. And so then the last one there is going to be nickel, which is just after iron, if I remember correctly. 2 after. Okay, so 28. It will have 2 valence electrons as well. So it would be 28 and 26. So nickel 28 minus 26, which is 2. You might be noticing a trend there. The effective nuclear charge is matching up pretty well with the number of valence electrons. And I do believe that is always going to be the case. As with all things in science, there's probably an exception to that somewhere. But for our purposes, it's pretty much going to, as far as I'm aware anyway, it's always going to hold up. That the effective nuclear charge will be the same as the number of valence electrons. So, this value, while interesting, doesn't actually tell us any specific trends. We're only going to be able to use these values to compare from one element to another, and that will help us figure out, comparing, for example, silicon and iron, comparing their effective nuclear charges, seeing the difference between the two. That will help us figure out, for example, which one of these two elements will be larger, or which one of them will have more electronegativity. It'll help us figure that out. So, speaking of which, let's go ahead and look at the first 4 things we're going to be considering here, the first 4 properties that vary across the periodic table. We're going to look at atomic radius, which, as the name says, is just the size of an atom. It's literally the radius of an atom, how large the atom is. Electronegativity is probably a term you've never heard before today anyway. And electronegativity is just the it's a measure of how strongly an atom attracts electrons, so how badly it wants electrons would be another way of putting that. Ionization energy is related to that, but it is different. Ionization energy is the amount of energy that it takes to remove an electron. So if you have to take an electron away from something, how difficult is it to do that? How much energy do you have to expend to do that? And then we have electron affinity as well, which is how likely an atom is to accept an electron. And then there's one other we're going to look at the very end. That's metallic character. So we will look at all 5 of these. Starting off here with atomic radius. So the atomic radius, like I said just a second ago, is just a measure of how large an atom is. There's 2 different directions on the periodic table that we're going to be looking at for all these trends. We're going to be looking at it in terms of, does it get larger or smaller going up and down the table, and does it get larger or smaller going across the table, going left and right across the table. Now going up and down on the periodic table is pretty straightforward. So why don't you stop for just a second and think about, for example, sodium and potassium, or oxygen and sulfur, and which one of those, which one of the pairs here, so either sodium or potassium, which one of those 2 is larger, and why? So if you're thinking about sodium and potassium, probably you said potassium is larger. And probably your reasoning for that was because potassium is a bigger atom in terms of the number of particles. It is just below sodium on the periodic table, and so it has more protons, it has more neutrons, it has more electrons, and so it should be bigger. And it is. So potassium is bigger than sodium. Sulfur is bigger than oxygen. Iodine is bigger than chlorine. And neon is bigger than helium. All for the same reason. As you're going down the periodic table, you get to larger elements, simply because there's more stuff. They have the same electron configuration, they just have an extra shell going down the periodic table. And so those are going to be larger as you go down, smaller as you go up the periodic table. Going across the table is a little bit different, though. So thinking about sodium and magnesium, which one do you think is going to be larger? If you use the same logic as the up and down on the periodic table, it seems that magnesium should be bigger. But it's actually not. Sodium is actually larger than magnesium, even though it has fewer particles. So to try and understand this, let's think about the effective nuclear charge. So the effective nuclear charge for sodium is 1. The effective nuclear charge for magnesium is 2. And if you don't believe me, you can go back and do the calculations on those. So what the effective nuclear charge is telling us is that the electrons, the outermost electrons in sodium, feel the nucleus less than the magnesium. They don't have as much of an attraction, so to speak, to the nucleus as they do in magnesium. The effective charge of the nucleus is larger in magnesium. What this means is that because when we go from sodium to magnesium, because we're not putting electrons into a different shell, sodium, if I remember correctly, that's going into the 3s. Yeah, so this would be 3s1. That's the last electron to go into sodium. Magnesium would be 3s2. So those 2 electrons, they're in the same shell together. They're not really any, and in fact they aren't any, farther away from the nucleus, one from the other. The first electron to go into the 3s is a certain distance away from the nucleus, and the next one that also goes into the 3s It's the same distance from the nucleus. But at the same time that you're putting another electron into the same distance from the nucleus, you're adding more positive charge to the nucleus. And so you're increasing the attraction to the nucleus, which is what you see there with the effective nuclear charge going up to 2. So you're not increasing the distance the electrons are sitting away from the nucleus, and at the same time you're increasing the pull from the nucleus on those outermost electrons. And so the net result is that as you go to the right on the periodic table, as long as you're staying in the same period, you will see elements get smaller. So smaller elements are on the right side of the table because the effective nuclear charge increases as you go to the right on the periodic table. So larger Z star will have smaller radius. And so why don't you pause the video for just a second here and work out what the larger elements would be in each of these pairs here. So go ahead and pause the video right now and see if you can work those out. Okay, so hopefully you paused the video and tried to work those out on your own. Hopefully you have a periodic table handy so you can do that. So if you look at the first pair there, scandium and iron, scandium is on the same period as iron, and it is to the left of iron. And so that would mean that scandium is the larger, because remember, things get smaller as they go to the right. Indium and tin. Let's see here, to find it on the periodic table myself. Where did it? There it is. So there's tin and indium are on the same period. Indium is farther to the left. And so indium would be the small, oops, I'm writing the larger ones, aren't I? Actually, yeah, wrote the right symbol and then started to say the wrong thing. So indium would be larger because it is farther to the left. All right, tin and lead. Lead is lower, but it's in the same row. It's in the same group as tin, and so lead would be bigger. Because again, if it's in the same column, the farther down you go, the larger. Oxygen and phosphorus. This is the first example we've seen where they're neither in the same row or column, the same period or column. And if we look at the two trends here, phosphorus is lower on the table than oxygen, and phosphorus is farther to the left on the table. And so both of the trends agree that phosphorus should be bigger. Same thing with phosphorus and potassium, but now it's potassium that is bigger, because potassium is lower and to the left on the table, much lower and much farther to the left, and potassium is in fact much larger than phosphorus. Magnesium and potassium. So potassium is, let's see here, it is down and to the left of magnesium, and so potassium is once again the larger. And then the last one here, we have carbon or chlorine. This is where it gets a little bit tricky because now the trends disagree. Chlorine is lower, which means the trend is telling us that chlorine should be larger, but carbon is farther to the left. When we have a situation like this where the two trends disagree, we are just going to say can't tell. So we can't tell based on the trends. So our overall trend then is things get larger going to the right and going up, or if you prefer to add those together, up and to the right. Things get larger. And so we can see that here if we actually have a diagram of different, all the atomic radii from hydrogen up to, boy, I don't know, it's past xenon, whatever that is. And as you can see here, the largest elements are all those alkali metals. By far, those are the largest ones. And those are all the way to the left on the periodic table. And as you start to go across the row, that atomic radius overall gets smaller and smaller and smaller with each of those rows. Now, obviously, there's a few exceptions here and there. Like, again, there's exceptions to almost everything in science. But overall, as you go to the right on the periodic table, things get smaller. And as you go down the table, things get larger. And you can see that here going from lithium to sodium to potassium to rubidium to cesium. It is getting larger and larger. Okay, I think we have just one more quick thing here. Actually, you know what? I think I'm going to save this for the next video because this has been a pretty long video at this point. So we will pick up here in the next one talking about atomic radii. So I'll see you all in the next one.